do for that?
Group 1.
You will get full marks.
Oh, yeah.
To C divided by 2 root mk. So it will come around 0.86, 0.816. And if you calculate by that, it will come, everything will fall into place.
Then that also won't for me.
If you are given step marks, I'll get 1 mark. I got the C value. After that, I left it off.
Roshan ji, I have used your sheet. I was putting some calculator. That answer was coming. So that I thought, okay, that might be the correct answer. Yes, sir. Yes, sir. Actually, and what happened, Valish, that bad part of me was I on the formula sheet I wrote the wrong this thing calculation. Formula. So I had to derive the formula at the classroom. So it took around 15 minutes. That's not the problem. So that's why in hurry I missed 2 wrong answers for last question here. Otherwise I could have also scored maybe better. I don't know.
Yeah, that will help us class.
You said something. True class leader.
He has to worry for all of us.
He's a true class leader. Yeah, true class leader. He has posted the marks or what?
Out of that, Roshan is the first one, no?
No, because
Sorry,
for,
between I missed it.
Roshan, the Rahul is there. Rahul.
Yes, sir. Yeah.
I think you also got 30 marks, na?
Yeah, I'm not sure, sir. I didn't check with the key and all.
Arey, Rahul, you will easily score 30
Your
marks.
paper is the answer. Whatever you have written is the answer.
See, whatever answer sheet I've said now, only except question number 15, everything is right.
So
15,
I think
15 will be C actually. 15 question answer will be C. Rest everything
what
is
is
right.
the 15th question?
That is like inner wheel. When a vehicle takes a turn, 4-wheel vehicle takes a turn. The four this thing was there, na?
Inner will have more angle.
Yeah, inner wheel will have more angle than outer.
Yes, that is C is the correct. I wrote B, so that was a mistake from my side. Rest everything
That
is
is the
right.
only answer I did it correct. That is the only answer. Immediately
Inner will cover more distance.
Outer will cover more distance. But inner will have more angle.
Yes, right.
Yes.
C is the answer.
Options like that.
C is the answer, right.
Inner will put us on I.
Next to, then you give the, before sharing, Professor, you can give the answer link.
Right. Let him only release answers.
Sir, one question ka answer kiya.
IC engine professor, given that
just one thing, one question here from the forum. Basically, the question number first was assignment 2. Assignment 2. Anand sir wala. In that, I think he has given wedge type of combustion chamber, if I'm not wrong.
Time up.
Not a problem.
Sir is coming any moment.
Okay.
He is talking about question only now.
Okay.
Question 2 is open already here. ಈಗ ಕ್ವಿಸ್ 2 ಓಡ ಕೀ ಓಪನ್ ಮಾಡ್ಬೇಕು. Is quiz is really quiz 1 key ಬರೆದಾರ ಪಕ್ಕ perfection ಅವ್ರು ಬರೆದ್ರೆ ವಿವಿಧ ಬಂತು
ಪಕ್ಕ ಇದ್ದಾರಪ್ಪ.
So much patience.
Exactly 10 for this exam. The probability of you getting correct in each and every question is 20.
Pinpoint areas.
Hello.
Sir, good evening, sir.
Good evening, sir.
Good evening, sir.
Good evening.
Sir, thanks, sir. We received a question. First quiz
Okay,
answer.
fine. So you can go through that for two things. One, to check the answers of the numerical problem. Second one, you can also check how to answer the theory questions.
Sure, sir. Sure.
Sir, wish you happy Holi, sir. Thank you. Wish you all a happy Holi too. Thank you, sir.
Thank you, sir. Same to you, sir.
Thank you.
So now you feel better?
Yeah. Now I'm feeling better. Yeah,
Thank you.
infection was there for 2 days. So in IIT campus, it is quite common that often there is some eye infection because a lot of trees are there. Basically, it is a tree-based pollen grains that will create some infection, especially for people who are allergic. Okay, I'm sharing my screen. Is my screen visible to you?
Yes, sir.
Yes, sir.
Okay, please answer your attendance. Aditya Kumar,
Present, sir.
Anand,
Yes, sir.
Ananda Kumar,
Yes, sir.
Arnachalam,
Yes, sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad, Lakshmi Narayana,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Ragul,
Yes, sir.
Raujan Kumar. Yes, sir. Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Vallish,
Yes, sir.
Vigneshwaran,
Present, sir.
Vijayaraj,
Yes, sir.
Vikash,
Present, sir.
Vivekanand, Yadav,
Yes, sir.
Yuvraj. Okay, three.
Sir, Keshav is present, sir.
Kesav Prasad is
Yes,
present.
sir.
Okay.
Yes, sir.
Vivekanand and Yuvraj have not answered. So there are two absentees today, Vivekanand and Yuvraj. Okay, welcome back. We have now moved to chapter number 4. Chapter number 4 deals with instrumentation to study the combustion process in IC engines, both SI and CA engine. So what we are going to look at here, these are the contents, overview of contents that we are going to discuss in this chapter, which I have already presented. So we are going to discuss the measurement principle followed to acquire the combustion data. Basically, you need a pressure profile. Pressure profile shows how the in-cylinder gas pressure varies with the crankshaft angular position. So you need these two instruments. One is a pressure measurement device and second one is an crankshaft angular position measurement device. With this, you can get this pressure profile, which is basic or important data, combustion data, which is also referred to as cardiograph of IC engine. It shows how well the pressure profile shows how well an engine, IC engine functions.
So this is the fundamental data that you need to have in order to analyze the combustion process in a SI as well as in CI engine. You need to have a pressure profile. So we need to get familiar with what instrument that we need to have to measure the pressure, what is the measurement principle involved. Similarly, we need to know how I can get the crankshaft angular position, what type of instrument I need, and what is the principle involved, measurement principle involved. So this we are going to discuss, and after this, we are going to discuss about how we can derive other parameters from the measured pressure profile. We will have this pressure profile. From the measured pressure profile, we are going to derive other parameters, combustion parameters. So all these parameters will be helpful to do combustion analysis in IC engines. Okay. So to enable combustion analysis, you need this measured pressure profile, and you need to know how I can derive other parameters from the pressure profile. This is what we are going to discuss in this chapter 4. Of course, it's a short chapter, and these are the contents that we will be discussing. So in the previous class, we have discussed that we measure instantaneous cylinder pressure. So we measure this instantaneous cylinder pressure and instantaneous crank angle. So what is instantaneous cylinder pressure? The in-cylinder gas pressure at any point of time. That is what is instantaneous cylinder pressure, and we need to measure the pressure with reference to crank angle, that is a crankshaft angular position. Again, it is instantaneous, meaning at any point of time. So when I say that at any point of time, we are not considering in absolute time unit. So this doesn't make any sense. This is what we have discussed. Pressure measured with respect to absolute time scale doesn't make any sense at all. Okay. But instead, what we do is we measure pressure in a crankshaft angular domain, crank angle domain. Meaning that instantaneous pressure is analyzed with respect to the crankshaft angular position. Time here is related to crankshaft angular position. Okay, so you can always convert this time in absolute unit into crank angle. Okay, T and theta are related through what? Through what T and theta are related?
RPM.
Yes, engine RPM. So these two are related through engine speed. So engine speed relates this time with angle, crank angle. Okay. So with this, you will be able to convert this angle, whatever you measure, into absolute time unit. But the pressure has to be analyzed with respect to crankshaft angular position, because what we deal with are reciprocating engine. So in a reciprocating engine, you know that this crankshaft angular position can be related to the linear position of the piston at any point of time. Okay, so meaning that when I say that I am analyzing P theta, variation of in-cylinder pressure with angle theta, I am analyzing pressure with respect to the position, linear position of the piston inside the cylinder, because this theta is related to y. Y is any instantaneous position. In fact, it's y theta. Y theta is any instantaneous position of the piston inside the cylinder. This is given by L plus A minus S, where L is a connecting rod length and A is the crank arm length, and S is this vertical distance connecting this point and this point. Okay, and this S can be obtained from theta. So it is equal to this distance A cos theta plus this distance. This distance will be L square minus A square sine square theta square root. So basically you are relating this y, which is linear position of the piston, with respect to theta. Theta is the crankshaft angular position. This is nothing but slider crank relation, because it's a reciprocating engine. Piston reciprocate and crank arm rotates. Okay, and these two are related through this. So I am analyzing how the in-cylinder gas pressure varies with respect to the crankshaft angular position in order to get information about the linear position of the piston. So this makes a lot of sense, because, for example, during expansion stroke, I need to know where the piston is when the gas pressure varies. Okay, so ideally, I would be able to extract maximum work from the IC engine if the maximum pressure occurs at the start of expansion stroke, meaning the piston should be at top dead center position at the start of expansion stroke. Okay, at this point of time, if I get the maximum pressure, P max, then I'll be able to extract maximum work from the IC engine. Okay, so this is just an example. So I need to know where the piston is with respect to the gas pressure. Okay, so I need to track the position of the piston with respect to pressure variation inside the cylinder. This is where this P theta based analysis is very useful. Basically, I am tracking the piston position when I analyze the in cylinder gas pressure. That's why we do this analysis of combustion pressure variation in an angle domain, not in an absolute time domain. And again, one more important point here is when I say angle, this angle needs to be measured with respect to a reference point. The reference point in IC engine combustion analysis is compression TDC position. You know, in a 4-stroke cycle engine, piston reaches TDC point 2 times in an engine operating cycle, once during the end of compression stroke and second time during the end of exhaust stroke. End of exhaust stroke we don't need for combustion analysis. We need to track the piston position at the end of compression stroke, because that is a period where the combustion is happening. So this compression TDC position is a reference point for our combustion analysis. So the angle, crankshaft angle, will be measured with respect to compression TDC position. This is again an important point you need to note down. We are analyzing pressure in an angle domain so as to track the piston position, point number 1. Second, when I say about angle, crankshaft angle, you need a reference point to measure the angle. That reference point is compression TDC position. Okay. So now we need to know how we can acquire this cylinder pressure, how we can acquire this crank angle, how we can get this compression TDC position. These 3 are required in order to get this pressure profile. Pressure profile is the profile that shows how the in-cylinder gas pressure varies with respect to crank angle. Okay, so to get this pressure profile, I need these 3 information. One, instantaneous cylinder pressure. Second one, instantaneous angle, crank angle. Third one, compression TDC position. Now let us see how we can get this 3 information. So before that, I'm giving you an overview of combustion instrumentation here in this picture. So what we have here is the injector. This is a fuel injector. Okay, this is a line, high pressure fuel line. Here you have one sensor. This sensor that we have is a piezo resistive type sensor. This is called fuel line pressure sensor. This sensor is required only if you have a mechanical fuel injection system. In a mechanical fuel injection system, this sensor, line pressure sensor, is installed to get information about this pressure in the high pressure line. This information is useful to derive start of fuel injection, dynamic injection in a mechanical system, right? So this is required only if you have a mechanical fuel injection system, because this will help you to get information about start of fuel injection. This may not be required if you have a CRDI system, common rail direct injection system. I will talk about how we can get the start of fuel injection from the line pressure sensor later on in the combustion analysis part. But here just take a note that the sensor is required only for a mechanical system, fuel injection system. For CRDA system, what you need is an in-cylinder gas pressure sensor, which is installed here in the cylinder head. And this senses the pressure of the gas inside the cylinder at any point of time in an angle domain, as we discussed just now. So this sensor senses the in-cylinder gas pressure, and this sensor type is piezoelectric. I'm going to discuss in detail about the working principle of this sensor. A piezoelectric sensor installed in the cylinder head is going to sense the in-cylinder gas pressure. Okay, the output from the sensor goes to an amplifier, charge amplifier. Charge amplifier here does 2 functions. Actually, it has an inbuilt filter which will filter out unwanted or noise signals. It also amplifies the signal that comes out of the sensor. Okay, the signal, the output signal from the pressure sensor is of very low magnitude. The amplifier amplifies that low magnitude signal, okay, and then transfer it to a data acquisition system. So this is a sensing unit, this is a signal conditioning unit, and the third one is a data acquisition system. And this system provides you signals, pressure signal or pressure profile, right, online when the engine is running. You can also record the signal and use it for data processing later on. So this sensor provides you the in-cylinder pressure. And you have another sensor here. This is used to measure the crankshaft angular position. This is called angle encoder, crankshaft angle encoder. This provides you the crankshaft angular position. This gives two signals, as you could see here. One is TDC signal, other one is continuous signal, continuous pulse signal. So this TDC signal is a compression TDC point, and this continuous signals provides the crank angle, crankshaft angular position. Okay, and this angle is measured with respect to this TDC point, meaning the counting of angle starts with taking compression TDC as a reference point. Okay, so here we have the pressure sensor, and here we have the encoder fixed in the crankshaft. Okay, that provides you the angle signal, crankshaft angle signal, and this provides you the pressure signal. So this angle signal, whenever one pulse, angle pulse reaches the data acquisition system, the system is triggered. So the system simultaneously occurs a pressure. So here you should note that this pressure has to be indexed with respect to angle. That is what you get here in the pressure profile. The pressure is at any point of time, the pressure value is referenced with angle value, crankshaft angle value, P theta. Okay, so you need to index this pressure value with respect to angle, crankshaft angular value. Okay, and this angle is measured with respect to compression TDC point. So this is an overview of instrumentation that we need to have, and our focus is on these two instruments. One is cylinder pressure sensor, other one is the encoder, crankshaft angular position sensor. So now let us look at the pressure measurement. What is the principle followed, and how we get the pressure signal by using this sensor. And the sensor that we use is called a pressure transducer. This is also called a pressure pickup or a pressure sensor. Okay, these are different names for the same instrument. Pressure transducer, pressure pickup, or a pressure sensor is what is used. So this is a photographic view, and this is a sectional view, okay, of the pressure transducer. And this diagram, line diagram, provides operating principle of this sensor. Okay, this is a line sketch that indicates the operating principle of this pressure transducer. This is a sectional view. This is a photographic view, and this view is shown for the crystal, piezoelectric crystal. Okay, the primary instrument that senses the pressure here is a diaphragm. As you could see here, there is a metallic diaphragm. Okay, wherein this metallic diaphragm is here in the photograph. And this sensor is fixed, as I said, in the cylinder head. In the cylinder head, you will have this sensor. It's very small and very compact transducer. The leading sensor manufacturer, pressure sensor manufacturers are Kistler and AVL. Okay, Kistler sensors are robust that we use in our lab also. Okay, so we have this small compact pencil-like instrument fixed in the cylinder head. That's what you are seeing here, and this senses the in-cylinder gas pressure. So here, what we are going to look at are with reference to the pressure sensor or pressure measurement. So this are the okay. So this our discussion will be confined to what are the requirements of pressure sensor, how it works. We are going to see the working principle and how we can mount the sensor. Okay, what are the considerations for mounting the pressure sensor in the cylinder head? And when we discuss about mounting, we will also talk about this temperature drift. There are two types of temperature drifts. One is short-term drift, other one is long-term drift. And then finally, we will discuss about the speccing or referencing with reference to pressure sensor. Okay, so these are the requirements of pressure sensor. One is it should have a better frequency response. You should have a better, the sensor should have a better frequency response. What do you mean by frequency response?
Basically, the data equation interval, like how frequently is capturing the data in that sense.
How frequently the data is obtained.
Right,
That's
sir.
what you are saying. Okay.
Right, sir. Right, sir.
So what is the time scale what is the typical time scale to acquire the data?
5 milliseconds.
5 milliseconds.
It will be milli or microseconds in that. So we can set it up. As you rightly said, sir, as you have discussed in the previous classes, that the combustion is very fast phenomenon, and it is probably happening in nanosecond most of the time.
Yeah,
a milli or
nanosecond,
microsecond.
even less than that. So the sensor should have a very high frequency response. You know, frequency is 1 upon time, right? In a simple terms, frequency is 1 upon time. So the sensor that we use to acquire the insulator gas pressure will have a frequency of around 200 kilohertz. So you can convert that into time. So it means it will be able to respond to changes that are happening at that very small time scale. The sensor will respond to the changes that are happening at a very small time scale. This is what I mean by better frequency response. That's why these equipments are very expensive. Okay, so it's highly dynamic. It needs to acquire the changes happening at that very small time scale. Okay, this is one of the important requirement of a pressure sensor. It needs to have a better frequency response. The changes, the pressure changes happening in the cylinder are happening at a very small time scale. So the sensor should be able to pick up that. It should be able to sense the pressure changes at that very small time scale. This is what I mean by better frequency response. Also, the sensor should have a better sensitivity. What is sensitivity?
It should capture even a small pressure changes.
Small pressure changes. Okay. Sensitivity is output by input in simple term. The output from the sensor is basically in terms of this PC. PC is picocoulomb. What is coulomb?
Charge.
Yeah, electric charge. Okay, so coulomb is an electric charge carried away by 1 amp current for 1 second. Okay, this is a definition for coulomb, and here we are talking about picocoulomb. Pico is 10 power minus 12. So you can imagine. So such a very small charge is being generated by the sensor with respect to the pressure changes. So sensitivity is output by input. So it generates an output of 2 to 50 picocoulomb. Okay, that is the electric charge for a particular pressure value. Okay, so 2 to 50 picocoulomb per bar is a typical sensitivity of the sensor. So sensor should be able to generate an output. Without output, you cannot sense the pressure value, in cylinder pressure value. So it has to generate a pressure output charge value for a given change in pressure. This is what I mean by better sensitivity. It should have a better thermal resistance. So this is again an important characteristic. Thermal resistance is important because, you know, inside the cylinder, the gas is at a higher pressure, higher temperature, and this pressure and temperature continuously varies in an engine operating cycle. Okay, starting from intake stroke to exhaust stroke, you have intake, compression, then during the end of compression, combustion gets started. Combustion continue to happen for a particular period of time, and then you have exhaust. So over this period of time, in a typical engine operating cycle, the temperature inside the cylinder continuously varies. And of course, the pressure and temperature are very high during the combustion period. So the sensor, since it is exposed to hot combustion gases, it should have the sufficient thermal resistance. Otherwise, it will fail due to high pressure and high temperature inside the engine cylinder. The sensor should not fail at that conditions. Okay, high pressure, high temperature condition. So it should have a sufficient thermal resistance. Otherwise, it's going to fail. This is the reason why we use piezoelectric type sensors. Piezoelectric type sensors. The line pressure sensor, what I have shown earlier, are strain gauge type sensors, which don't have the sufficient thermal resistance. Piezoelectric type sensor will have sufficient thermal resistance. That's the reason it is expensive, and it's also used for in-cylinder gas pressure measurement because of its high thermal resistance. The signal produced by the sensor should be of repeatable nature. It should have a very good repeatability, okay, so that you get a reliable data from the sensor. It should not produce different values at different time. Linearity. The sensor is produced sensor output is an electric signal charge. Just now I have shown for a given change in pressure, and this should be linear. What will be the problem if these two are non-linear?
Then you have to then you will not get any correlation of data, sir, because then you have to find what is the curve equation,
Yeah.
and then you have to.
So the problem with the non-linear correlation is you need you need to extract multiple constant. Okay, multiple constant, and the output and the input, if at all it has a non-linear correlation, okay, it is going to create problems in terms of calibrating the sensor. Okay, we need to have a linear relationship. Generally, the sensor are calibrated with an equipment called dead weight pressure sensor, dead weight gauge, wherein you apply a known pressure, known pressure, and then measure the output from the sensor. Okay, since the pressure value is known, the output value is correlated with the applied pressure, known pressure. And we need to have a linear correlation between these two in the sense input, which is pressure, and output, which is an electric signal. So if these two are linearly correlated, the problem is less simple. Okay, if it is non-linear, then you need to do calibration at multiple points in order to get the calibration constants. Okay, so you will end up in having inaccuracies in the data that you obtain if you have a non-linear correlation. To avoid that, it's better to have a linear correlation. Now let us look at how the sensor working principle of the sensor. So this schematic line diagram shows how the sensor works. Okay, so what we do, we expose the sensor end. This end is having a diaphragm, metallic diaphragm, as you could see here. This metallic diaphragm is exposed to the combustion gases. Inside the cylinder, you have gases. Okay, when this metallic diaphragm is exposed to the combustion gases, okay, the gases exert a pressure on the diaphragm because it is at a higher pressure than the ambient pressure, right? So this gases exert a pressure on the metallic diaphragm. The diaphragm deflects, as you could observe here, because of the applied pressure. The applied pressure makes the diaphragm to deflect. Okay, and this deflection is transmitted to the sensing element. Sensing element of the sensor is this crystal. This is a piezoelectric crystal, okay, shown separately here. It's a piezoelectric crystal. The diaphragm get compressed due to the application of the pressure, in cylinder gas pressure, and this is transmitted to the crystal. The crystal in turn will get compressed. And this crystal is a piezoelectric crystal. And the transmission of signal happens through this intermediate element. Through this intermediate element, the change in pressure experienced by the diaphragm is transmitted to the quartz crystal, which gets strained or compressed by a rate d epsilon by dt. dp by dt is the applied pressure. Due to rate of change of pressure, which is dp by dt, the diaphragm deflects and that is transmitted to the crystal. The crystal gets deformed at a rate of d epsilon by dt. Once the crystal deforms, because of its property, it is charged actually. You could see that the opposite ends are oppositely charged, positive charge and negative charge. The compression of the crystal by an amount equal to d epsilon by dt generates a charge. Okay, so here you have electrodes in contact with the crystal. Okay, and this effect is called piezoelectric effect. Whenever a piezoelectric crystal is subjected to a strain, right? Subjected to a strain, it generates electric charge. It's a property of this crystal. Okay, it generates electric charge. The electrodes which are in contact with the crystal, okay, carries this charge dq by dt to an external circuit. So this is where the pressure is applied. Okay, because of the application of the pressure inside the cylinder, inside the sensor, you have the quartz crystal, which generates an electric charge, and the charge is carried away through this cable. It's highly insulated coaxial cable, right? Through this cable, the charge is transmitted to the external circuit. Okay, the charge the current in the, so there is a flow of current in the external circuit. Okay, because of dq by dt, q is charge. I is equal to dq by dt, and this charge is generated primarily because of the pressure dp by dt. So we can say that this I in the external circuit is equal to rate of change of charge dq by dt, which is equal to rate of change of pressure. Okay, and this is directly proportional to pressure, and you have a constant here, which is a sensitivity of this equipment. GS is the sensitivity of this equipment. So this is what is happening here. So you apply pressure on the diaphragm, dp by dt is applied pressure. Because of that, the crystal gets strained by d epsilon by dt. Because of the strain, you generate an electric charge dq by dt. So there is a flow of current I in the external circuit, and this I is proportional to dp by dt. To remove the proportionality symbol, you introduce a constant, which is sensitivity of the equipment. So this is I is equal to dP by dt multiplied by GS. GS is the sensitivity of the equipment. Okay, so we are tracking this I that flows in the external circuit. Okay, so from here it goes to this. So you sense the pressure in cylinder pressure, okay, it generates a current, and this current goes to a charge amplifier which amplifies this current at the input, okay, it amplifies the signal and produces an output signal which is correlated with the pressure in cylinder gas pressure, right? This output is an electric signal which is correlated with the in cylinder gas pressure. This is how you connect this electric signal output to the input. Input is the pressure inside the cylinder.
Sir, this GP constant, sensitivity
GS.
constant, GS,
Mhm.
that seems to be a constant value in this equation. But whether in practical sense, does it remain constant throughout the application?
So what you do, how you will get this is, I will come back to that. How you will get this value is through calibration, as I said.
Okay, okay, sir.
So you need to calibrate it at multiple points. So with known applied pressure, you need to track the output voltage. And generally, as I said, we need to have a linear relation between the pressure and the electric signal.
Thank you, sir. Thank you so much.
Generally, these piezoelectric crystals have very good linear response, very good linearity. This is again one of the reasons why we use this. That's why only very few companies have mastered this in-cylinder gas pressure measurement. I said AVL and Kistler. These two people are pioneers because of because although it looks simple, it is actually a complex thing. Okay, so you need to satisfy all this requirement, right? Even if one of the requirement fails, the sensor won't work well. The problem is the changes in the cylinder are happening at a very small time scale. Okay, but generally piezoelectric crystals have a very good linear response. And you need to calibrate to get the constant values, sensitivity values. So with respect to, so this is how the sensor work, and with respect to mounting, we mount the sensor in the cylinder head as shown here in the schematic. So it is located in the cylinder head. Okay, where do we locate is an important point to be considered. And one of the important aspect that we need to look at when we mount the sensor is, it's preferable to mount the sensor, we call it as flush mounting. What is this flush mounting? You could see that the bottom end of the sensor diaphragm aligns with the lower end of the cylinder head. This is what I mean flush mounting. This is preferable because you are exposing the diaphragm directly to the in-cylinder gas pressure. Okay, so the accuracy will be more because the sensor is directly exposed to the in-cylinder gas pressure. It avoids any time lag in acquiring the signal, and generally the sensor is mounted at a point wherein you have a maximum mass concentrated. Generally above the piston bowl, most of the mass, in-cylinder mass is concentrated. So you locate this sensor at that point, okay, at the point where you have access to the maximum mass, in-cylinder mass. Okay, and it is preferable to have a flush mounting as shown here in the simple drawing. The lower end of the diaphragm is aligned with the lower end of the cylinder head. This is what I mean by flush mounting. But there is a problem that occurs with flush mounting, which is referred to as drift, temperature drift. What happens is inside the cylinder you have higher temperature, and the temperature also continuously varies over an engine operating cycle. Okay, so you have something called a transient heat flow in the cylinder. What is transient heat flow? The heat flows into the sensor continuously varies with respect to time in one operating cycle. You know, engine execute n number of operating cycle based on the engine running speed. Even within an operating cycle, one operating cycle will be few milliseconds. Okay, and this few millisecond or microsecond depends on the engine running speed, the time required to complete one cycle. Even within an engine operating cycle, you know the temperature continuously varies. starting from intake stroke to compression stroke to combustion period and expansion and exhaust period, the temperature continuously varies. That's why there is a transient heat flow from the gases to the sensor. What happened because of this transient heat flow, the sensor elements, including the diaphragm and the entire housing, transducer housing, is subjected to thermal stress, continuous variation in the thermal stress. Okay, so because of this thermal stress, varying temperature in the cylinder, the temperature inside the cylinder continuously varies, and this results in the expansion of the sensor elements, including diaphragm. And this leads to something called a signal distortion. The signal distortion. The pressure output gets distorted because of the transient heat flow that creates thermal stress, continuously varying thermal stress on all the elements of the transducer. And there are two types of drift. This is what is meant by drift. Drift is signal distortion due to temperature variation, right? The temperature variation is due to transient heat flow. The sensor elements are subjected to temperature variation due to transient heat flow, and this results in signal distortion. And this signal distortion is referred to as a drift. There are two types of drift. One is short-term drift and other one is long-term drift. Short-term drift is due to cycle by cycle variation. So, you know, we already discussed about cycle by cycle variation. Cycle by cycle combustion variation is more severe in SI engine compared to CA engine. So from one cycle to other cycle, the temperature changes. And because of this change in temperature from one cycle to other cycle, there is a drift, and that is referred to as short-term drift. Long-term drift is, generally this happens quickly, short-term drift due to cycle by cycle variation. Long-term drift happens slowly, and this is due to change in operating condition. For example, when you take the engine from a low load to high load, okay, there is a sudden change in the pressure and temperature condition. When you move towards high load, the temperatures are so high. So the variations in in-cylinder temperature or transient heat flow due to change in engine operating condition results in long-term drift that happens slowly. The variations in transient heat flow due to cycle by cycle variation is referred to as short-term drift that happens quickly. The overall effect of the drift is, as I said, signal distortion. When the drift is severe, it is going to damage the sensor. How do I know that the sensor is damaged? You could see that during the exhaust stroke, the sensor output in terms of pressure will be lower than the ambient pressure. You know, during the exhaust stroke, the pressure is never below ambient, right? The pressure is always above ambient, even during exhaust stroke. Few bar above, 3 to 5 bar will be the typical pressure, exhaust pressure. At the time of exhaust process, the pressure is around 3 to 5 bar. Okay, it's always higher than the ambient pressure. Because of the drift, the sensor, if at all it is damaged, during that period of time, it will show pressure value below ambient pressure. That is an indication that the sensor is damaged. This is the effect of this temperature drift, and this primarily happens due to transient heat flow, which you cannot avoid. The sensor has to withstand the temperature variation. But what you can do is, you cannot avoid, but you can minimize the effect of the drift by doing certain changes. One is you have to mount the sensor in the well-cooled regions of the cylinder head, point number one. Point number two, you can take the sensor in by few mm as shown here, 1.5 to 3 mm, right? Don't do the flush mounting, meaning don't align the sensor lower end with the lower end of the cylinder head. Instead, take in few mm, 1.5 around few mm. Okay, when you take in, you are not directly exposing the transducer sensing element to the high pressure, high temperature gases. So the effect of transient heat flow will get minimized by taking in sensor few mm. Okay, this is one thing. And second one, as I said, you have to mount it in a well-cooled regions of the cylinder head. And the third thing they will do is, you could see here on both sides of the sensor, so you could see here, these are the coolant flow passages. So on both ends. So this is coolant flow passages. So you will circulate cooling medium, generally water will be circulated, okay, to keep the temperature of the sensing element within the limit, within the design limit, okay. Due to transient heat flow, as I said, the sensor elements are exposed to hot combustion gases and temperature variation, which will result in expansion of the sensor due to high temperature. Okay, so by providing sufficient cooling system, there are two types of sensor: air cooled and water cooled. Generally, this water cooled sensors are recommended if the in-cylinder gas pressure and temperature are very high. Okay, durability of this sensor is high compared to air cooled sensor. So this is what you are doing here. One is avoiding flush mounting to minimize the effect of transient heat flow. You take in few mm. Second one, provide sufficient cooling. Also locate this sensor in the region of the cylinder head where you have minimum temperature, operating temperature. But what will happen when you take the sensor in? What is the limitation of taking in the pressure sensor? Or in other words, if you don't do flush mounting, what limitations or shortcomings you can expect?
The pressure will be not so exact as present in the combustion chamber.
Okay, so here it is directly exposed in the flush mounting. Here, yeah.
Sir, normally in combustion chamber inside 1000 degree Celsius above it will be there. This coolant you previous slide you have shown the coolant, no sir, coolant circuit. How efficient it will be, sir?
How efficient coolant circuit? What coolant circuit you are talking here?
Earlier page that diagram you have shown.
Around the sensor,
Sensor.
Okay. So no. The temperature is inside the cylinder, right? Sensor won't be at that very high value.
Anyway, gas will be that. It will have that.
So only sensing element is exposed to that high value. Okay, the diaphragm, metallic diaphragm. The rest of the element won't be at that higher temperature, 1000 degree. 1000 degree is not possible. Okay. It will be at a much lower temperature, not exactly the in-cylinder gas temperature. In-cylinder gas temperature will be much higher. Only the sensing element, right? This sensing element, which is a diaphragm, metallic diaphragm, will be exposed to hot gases. But
so
the
what
rest
material
of the elements,
what material it will be, sir? It will withstand that much temperature.
it's a metal actually. Metal, the material that will be used for that metal will be based on the operating temperature. Generally, it is an alloy. Okay, that alloy proportion is based on the engine operating temperature. You have sensors available with different specifications based on the operating pressure. They will calculate the operating temperature. Accordingly, the material will be decided.
Okay, sir. Okay. Sir, one more thing. Normally, if we are measuring cylinder pressure, no, if it is a 4-cylinder engine, we will put first cylinder or we will put in 6-cylinder only.
It doesn't matter. So it is recommended to put sensor in all the cylinders, especially in SI engine, because you will have more cylinder to cylinder variation. So we talked about cycle to cycle variation. There will be cylinder to cylinder variation also if the mixture distribution is not even. See, in a SI engine, you are injecting fuel outside the cylinder, right? So there are possibilities that you may not get a uniform equivalence ratio or uniform fuel air proportion in each cylinder. Whereas in CI engine, you are directly spraying the fuel into cylinder at the end of compression stroke. Okay, the variations are minimal. I mean, cylinder to cylinder variations are minimal in a CI engine compared to SI engine. So it is better to sense in cylinder pressure in all the 4 cylinders, especially for SI engine.
Okay, sir. Okay. Thank you, sir.
So here, when you mount the sensor, when you take in few you are actually creating a passage here. There are problems here. Although you minimize the transient heat flow effect, the problem is through this channel or a small passage, you may have pressure oscillations. This pressure oscillations may result in some inaccuracies in the pressure value measure. Also, since the sensing element is not directly exposed to gases, okay, it is not directly exposed, there may be some time lag. But the time lag is generally minimum because pressure is a wave phenomena. Pressure will equilibrate quickly. Wherever there is a pressure difference, it will try to equilibrate as quickly as possible. Okay, that is one advantage here. Okay, it won't affect much, but nevertheless, there will be some time lag as compared to the flush mounting. Although these problems are there to avoid the effect of drift, which is more severe thing, right? We do this kind of mounting of pressure sensor. Okay, also we need to provide sufficient cooling to the sensor. The last point is about pegging or referencing. In principle, whatever the sensor output that you get is pressure difference. Okay, pressure difference. Now, in order to get the actual pressure value, by design, the transducer, whatever output you get, because as I said, this I is related to dP by dt, not P. It is dP. Okay. So by design, this is how the sensor is designed. By design, the transducer measures the pressure difference. Okay, not the absolute value of pressure, it's a difference or relative pressure. Okay, it will take some arbitrary starting point. Arbitrary starting point may be the point at which the sensor gets started or reset. Okay, that is an arbitrary time instant. The amplifier, where the signal output from this pressure sensor goes to an amplifier, and the amplifier has an integrated circuit. That integrated circuit will integrate the input current value over a period of time. So it starts from some arbitrary pressure value or from arbitrary time instant. That is how you get dP here. Now, in order to get the actual value, pressure value, what is generally done is the pressure output from the sensor is correlated with some known pressure. The output from the sensor is correlated with some known pressure in the engine operating cycle. Okay, the known pressure generally taken or considered is pressure at bottom dead center during the end of intake stroke. During the end of intake stroke, the pressure, the piston will be at bottom dead center. The pressure in the cylinder will be almost equal to pressure in the intake manifold. Did you get what I am saying? During the end of intake stroke, the pressure in the cylinder. So this is intake manifold. This is BDC point. Okay, piston moves down during intake stroke. When the piston is at BDC, that is end of intake stroke or start of compression stroke, the pressure here and the pressure in the cylinder are almost same. Okay, these two values are same. The pressure in the intake manifold can be measured with some other equipment. Okay, this is what I mean by known pressure. You are actually getting the sensor output, right? Sensor output adjusted for a known pressure value. Known pressure value is the pressure in the cylinder when the piston is at bottom dead center. That is at the start of compression stroke or end of intake stroke. Okay, you are adjusting the sensor output with this known value. Okay, by doing this, actually you are getting the actual value. Actual value. This process is called as referencing or pegging process. So you are actually adjusting the output from the pressure sensor with some known pressure value. The known pressure value is the pressure in the intake manifold measured with some other equipment. Okay. So otherwise, what you will get pressure difference, and the pressure difference is based on some arbitrary initial pressure value. Rather than doing that, you are correlating it with some known pressure in the engine operating cycle. And this process is referred to as pegging or referencing. So whenever you install a new pressure sensor, you need to carry out this pegging process. Next, here we are going to look at how we can get the angle, crankshaft angular position. To get crankshaft angular position, the equipment used is called crank angle encoder. Okay, this is a typical crank angle encoder. It's a transparent disc. Okay, this is a photographic view of the encoder. It consists of a transparent disc, okay, shown here separately. This transparent disc consists of n number of thin lines. These lines are opaque line, meaning light cannot pass through the line. Okay, so you have n number of thin opaque line at equal angular intervals, around this transparent disc. And you have one more mark, okay, thin mark. And this mark is correlated with the compression TDC position. So we measure angle considering compression TDC as a reference point. So you have one mark to indicate compression TDC, continuous marks to indicate the crankshaft angular position. Okay, so and this disc is fixed along with the crankshaft, meaning this is going to rotate along with the crankshaft. And these lines are opaque, meaning light cannot pass through. So what is done during an operation? Light from an LED source, as you could see here, light from an LED source is allowed to pass over the transparent disc in a perpendicular direction. So it is perpendicular to the disc plane. Perpendicular to the disc plane, light from an LED source is allowed to pass. Whenever the light meets this opaque line, since they are opaque, the light is going to get reflected back. Whenever the light meets the gap between the two lines, it's going to pass through. Did you get what I'm saying?
Yes, sir.
Yes, sir.
When the light meets the line, which is an opaque line, the light is going to get reflected back. But when the light meets the gap between the two lines, subsequent line, the light is going to pass through. So you allow light from an LED source, okay, impinge on this transparent disc, okay, perpendicular direction. So when you do this, you're going to get a sequence of light pulses synchronized with the crankshaft angular position. So you will going to have a n number of light pulses passing through this based on the crankshaft angular position. Okay, and this light pulses will be conducted through an optical fiber. This light pulses are conducted, and from there it goes to light to electric pulse converter, which is a typical PV photovoltaic cell. You can use a photovoltaic cell to convert a light signal into electric signal. So this photovoltaic, what it will do, it will convert each light pulse into an electric pulse. So you will have a sequence of light pulses conducted through the optical fiber, and it goes to light to electric pulse converter, which produces n number of electric pulse signal. And this pulse signal, number of electric pulse signal correlate with the crankshaft angular position. Okay, and there is a separate counter. The counter will count the number of pulses, and that is an indication of the crankshaft angular position. Now, to count the angle, you need a reference point. That reference point is this. This one is the compression TDC mark. Okay, we are counting the angle based on this compression TDC mark. The general practice is we will take compression TDC as a 0 degree, and anything after compression TDC will be positive angle. Anything before that will be considered as a negative angle. Okay, that we will discuss later on when we do the combustion analysis. So, okay, but the point to be noted here are we are getting a continuous angle signal, crankshaft angle signal, and there is one signal for each revolution that corresponds to compression TDC point, and there are n number of signals that corresponds to crankshaft angular position. We count the angle considering this as a reference point, compression TDC as a reference point. Okay, that is how this angular encoder gives you the crankshaft angular position. Okay, so we use this device to get the information about the crankshaft angular position. As I said in the beginning, so you will have this one TDC signal from the encoder and then continuous angle signal. Okay, TDC and continuous angle signals are the output from this crankshaft angular encoder. Okay, and for each pulse, the high-speed data acquisition system will be triggered so that you simultaneously acquire the pressure value. So each pressure value is correlated with this angle value. Okay, and this angle measurement is done taking this mark as a reference point. Okay, that is how you get the pressure and angle. That is how you sequence this pressure value with the angle value. It's time up. I stop here. If you have any questions, I can take them. Are there any doubts?
So what will be the gap between that incremental lines, sir?
Okay, the gap between, it's a good question. The gap between the incremental line will be based on the resolution you want. Suppose if you want 0.5 degree angle resolution, how many signals you need to acquire? Did you get what I am saying? 0.5 degree resolution, meaning you are acquiring pressure for each 0.5 degree crank angle data.
360 divided by 5.
For 1 degree resolution, you need 360 angle data, right?
Yeah, it is 720.
Into 2, sir. 720.
No, into 2, 720. Okay. So based on the resolution, if it is 0.1, then 720 into 10. So there are also something called pulse multipliers that are available that will help you to get more resolution. I mean, finer resolution. So the gap is based on the resolution that you need to have.
And typically, what is the value, sir, for this resolution?
Typically, we will go with even 1 degree accuracy for some of the engine, and 0.1 is also used for some of the engine. It It depends on the type of engine and the type of data you acquire. For example, for dP by d theta, it's a derivative of the pressure, right? Finer resolution is better if you go for derivative of the pressure. P theta, you can even go with 0.5 degree. 0.5 is generally fine.
Okay, sir. Thank you.
Okay. So I'll stop here. I will see you tomorrow at 6 o'clock.
Sir, just
Sir, one
more
question.
point, sir.
Yes.
Regarding the assignment 2, will it also be possible for you to share the lecture notes for chapter 3? It will be useful for us for the diagrams and all.
Okay. So up to my lecture notes are shared until when? Do you have?
I think till chapter 2.
Chapter 2
for quiz 1.
Up to quiz 1, sir. Up to quiz 1. Yes.
Up to quiz 1, I have shared. Okay. After quiz 1 information, I need to share. Lecture notes, I need to share. Okay. I will send it to you.
Okay, sir. Right. Thank you.
Okay. Fine.
And sir, this quiz will be more of, like would say, theoretical question based, right, sir?
There will be problem, simple problem. The type of problem I have given a hint through the assignment. Okay, so that kind of problem you can expect, and theory questions are basically to check the concepts.
Thank you, sir. Thank you so much.
Okay. Thank you. I'll see you. Yeah. Yes.
Sir, one query with respect to the position of pressure measurement sensor. Like as you told, to avoid drifting and unnecessary problems, the sensor to be placed in a well-cooled region. But considering the end gases at the cylinder wall area and the phenomena of knockings and all, is there any recommendation to position it closer to spark plug, or will it be done through calibrations?
The position of the sensor is based on how you design the coolant passages in the cylinder head, and that is typical for different engine types. You know, based on the heat load, the coolant passages are designed in the cylinder head, right?
Yes, sir.
You are going to locate the sensor based on how you design coolant passages in the cylinder head region, not in the wall region, in the head region.
Okay. So ideal case,
it's preferable to locate the sensor nearer to the coolant passage, so that the temperature is under check. Okay, so wherever you have the passage, coolant passage in the cylinder head, you can locate the sensor closer to that to keep the temperatures under check. Don't keep it far away from the coolant passage. That is going to create more transient heat flow. The temperature will slowly rise. As some of you asked whether the temperature will go to 1000 degree. It won't go, but right? The purpose of having the coolant in the cylinder head is to keep the temperature in the head under control. Okay, so you locate the sensor nearer to the coolant passage so that you keep a check on the temperature rise with respect to time.
Okay, sir. So the assumption is ideal case, the pressure, max pressure, peak pressure will be same all over the inside the engine cylinder, right?
Yes. Pressure will equilibrate quickly. That is what I said. Pressure won't vary locally. So there is locally the temperature will vary. Temperature will vary a lot from one location to other location because temperature will take more time to equilibrate. Okay, from the wall region, if you move towards the axis region, the temperature will vary significantly. But from the wall region, if you move towards the center of the cylinder or axis of the cylinder, the pressure doesn't vary much.
Okay, sir. Understood.
Okay, I'll stop here. I will see you tomorrow at 6 o'clock. Thank you.
Thank you.
Thank you, sir. Thanks a lot, sir.